Chi-square test. Chi-square test is an important test among the several tests of significance developed by statisticians. It was developed by Carl Person in 1900. Chi-square is a non-parametric test not based on any assumption or distribution of any variables. This statistical test follows a specific distribution known as chi-square distribution. In general, the test we use to measure the difference between what is observed and what is expected according to an assumed hypothesis is called chi-square test. Important characteristics of chi-square test. This test, as a non-parametric test, is based on frequencies, not on the parameters like mean and standard deviation. The test is used for testing hypotheses and is not useful for estimation. This test can be also applied in complex contingency table with several classes and such as a very useful test research work. This test can also implement non-parametric tests as no rigid assumptions are necessary regarding to type of population, no need for parameter values, and relatively fewer mathematical details are involved. Application of chi-square test. Chi-square goodness of fit test. A chi-square goodness of fit test is a type of chi-square test. You can use it to test whatever observed distribution or categorical variables differs from your expectation. Goodness of fit is a measure of how well the statistical model fits a set of observation. When goodness of fit is high, the value expected based on model are close to the observed values. When goodness of fit is low, the value expected based on the model are far from the observed values. The statistical model are analyzed by chi-square goodness of fit test are distributions. They can be any distribution from a simple as equal probability of all groups to as a complex as a probability distribution with many parameters. Chi-square goodness of fit test hypothesis. Like all hypothesis tests, a chi-square goodness of fit test evaluates two hypotheses, the null and the alternative hypothesis. There are two competing answers to the question: was the sample drawn from a population that follows the specified distribution? Null hypothesis: the population follows a specified distribution. Alternative hypothesis: the population that not follows the specified distribution. Null and alternative example. Null hypothesis: the dog population chooses the three flavors in equal proportion. P1 equals to P2 equals to P3. Alternative hypothesis: the dog population does not choose the three flavors in equal proportions. Example of chi-square goodness of fit test. You are hired by a dog food company to help them test three new dog food flavors. You recruit a random sample of 75 dogs. Over each dog, you choose between the three flavors by placing bowls in front of them. You expect that the flavors will be equally popular among the dogs, with 25 dogs choosing each flavor. Once you have your experimental result, you plan to use the chi-square goodness of fit test to figure out whether its distribution of dogs flavor chooses is significantly different from expectation. After a weeks of hard work, your dog food experiment is complete and you compiled your data in a table.
The chi-squared formula, where x squared is the chi-squared test statistic, is the summation operation. It means take the sum of O is the observed frequency and E is the expected frequency. The larger the difference between observation and the expectation, O minus e in the equation, the bigger the chi-squared will be. To use the formula, follow these 5 steps. First, create a table. Create a table with the observed and expected frequencies in 2 columns. Step 2, calculate O and E, or observed minus expected frequency. Add a new column called O minus E. Subtract the expected frequencies from the observed frequency. Step 4, O minus E squared divide into E. Add a final column, O minus E squared divide E. Divide the previous column by expected frequency. And lastly, step 5, calculate x squared. Add up the values of the previous column. This is the chi-squared test statistic. X squared equals 0.36 plus 1 plus 0.16 equals 1.52. Ang 0.36 plus 1 and plus 0.16 dirito na sa gikuha sa last column, which is amo ni ang 0 minus e squared divide into e. Baliging add na lang sila ang 0.36 plus 1 plus 0.16 equals 1.52. How to perform the chi-squared goodness of fit test. The chi-squared statistic is a means of goodness of fit, but on its own, it doesn't tell you much. For example, is x squared equals 1.52, a low and high goodness of fit. To interpret the chi-squared goodness of fit, you need to compare it something. That's what a chi-squared test is, comparing the chi-squared value to appropriate chi-squared distribution to decide whether to reject the null hypothesis. To perform a chi-squared goodness of fit test, follow the 5 steps. The first 2 steps have already been completed for the dog food example. Step 1, calculate expected frequencies. Something calculating the expected frequencies is the most difficult step. Think carefully about which expected values are most appropriate. If your null hypothesis in general, you'll need to multiply each group expected proportion by the total number of observations to get expected frequencies. Step 2, calculate chi-squared. Calculate chi-squared value from your observed and expected frequencies using the chi-squared formula. Step 3, find the critical chi-squared value. Find the critical chi-squared value in a chi-squared critical value table of using statistics software. The critical value is calculated from a chi-squared distribution. To find the critical chi-squared value, you'll need to know 2 things. The first thing is the degree of freedom, or DF. For chi-squared goodness of fit, the DF is the number of group minus 1. The second one is significant level, or A. By convention, the significant level is usually 0.05. Example, find the critical chi-squared value since there are 3 groups: the garlic blast, blueberry delight, and menti munch. there are two degrees of freedom. df, or degrees of freedom, equals r minus 1 and c minus 1. 3 minus 1 and 2 minus 1 equals 2. For a test of significant of A equals 0.05 and df equals 2, the x squared critical value is 5.22. And the step 4, compare the chi-squared value to critical value. Compare the chi-squared value to critical value to determine which is larger. For example, comparing the chi-squared value to critical value, x squared minus 1.52, critical value is 5.99. The x squared value less than critical value. In step 5, lastly, decide whether to reject the null hypothesis. If the x squared value is greater than the critical value, then the difference between the observed and expected distribution statistically significant, p greater than a. Data allow you to reject the null hypothesis and provide support for alternative hypotheses. If the x squared value is less than critical value, then difference between the observed and expected distribution is not statistically significant, p less than a. The data doesn't allow you to reject the null hypothesis and doesn't provide support for alternative hypotheses. Example, deciding whether to reject the null hypothesis. The x squared value is less than the critical value. Therefore, you should not reject the null hypothesis that the dog population chooses the 3 flavors in equal proportions. There is no significant difference between the observation and expectation flavor choice distribution. P greater than 0.05. This suggests that the dog food flavors are equal population than dog population.
A chi-square test of independence. A chi-square test of independence is a non-parametric hypothesis test. You can use it to test whether two categorical variables are related to each other. You can use a chi-square test of independence, also known as a chi-square test of association, to determine whether two categorical variables are related. If two variables are related, the probability of one variable having a certain value is dependent on the value of the other variable. Ang chi-square test for independence, amo ni siya is ang non-parametric hypothesis test. Ginagamit ni siya kung gusto nato mabalaan ang relationship sang duwa ka categorical variables. Amo ni siya ang alternative sa correlation coefficients. For example, ikaw bi isa ka researcher kag naga-conduct ka sang study kag gusto mo balaan kung may relationship ang socio status economic ka sang isa ka voter pakadto sa iya presidential bet sa upcoming election. Ang socio-economic status amo ni siya ang ga-categorize sa tatlo ka level. Amo ni siya ang low, medium kag high. Ordinal sa nga data ang tawag sa tatlo ka categories like sa variables na gina-compare sa presidential bet. Ang presidential bet nominal naman niya siya ang presidential bet nominal naman ni siya kay ngala ni siya ka candidate, like for example si Juan kag si Pedro. So manotice nyo man parehas ang categorical data, ang ordinal kag nominal hindi nato pwede gamiton basta-basta. Correlation coefficient kag gusto nyo mabalaan ang relationship diri masulod ang ginatawag nga chi-square test for independence. Amo na isang example, guys. Chi-square test of independence hypothesis. The chi-square test of independence is an inferential statistical test, meaning that it allows you to draw conclusions about a population based on example. Specifically, it allows you to conclude whether two variables are related in the population. Like all hypothesis tests, the chi-square test of independence evaluates a null and alternative hypothesis. The hypotheses are two competing answers to the questions are variable 1 and 2 are related. Ang chi-square test of independence naman hypothesis amo naman ni siya ang ginatawag nga inferential statistical, meaning na bala ng pwede ka makadraw conclusion about sa population based sa sample. Kag pwede man ma-end if ang duha ka variables related sa population. Null hypothesis. Variable 1 and 2 are not related in the population. The proportions of variable 1 are the same for different values of variable 2. Alternative hypothesis. Variable 1 and 2 are related in the population. The proportions of variable 1 are not the same for different values of variable 2. Ang null hypothesis, amo naman ni siya ang variable nga 1 kag 2 nga hindi sila related sa population. But ang proportions sang variable 1 are the same for different naman siya values sang variable sang 2. Ang alternative hypothesis niya baliskad naman siya sa null hypothesis. Kaya ang alternative hypothesis amo naman ni siya ang variable 1 kag 2 na related sila sa population kag ang proportion naman sa variable 1 hindi naman the same para sa different values of 1 and 2 nga variable. Added lang gali ang null hypothesis wala siya effect sa population. Kag ang alternative hypothesis may ara siya effect sa aton nga population. Example, chi-square test of independence. Imagine a city wants to encourage more of its residents to recycle their household waste. The city decides to test two interventions, an educational flyer, pamphlet, or a phone call. They randomly select 300 households and randomly assign them to the flyer. Phone calls or control group, no intervention. They use the results of their experiments to decide which intervention to use for the whole city. The city plans to use a chi-square test of independence test to test whether the proportion of households who recycle differs between the interventions. Contingency tables. When you want to perform a chi-square test of independence, the best way to organize your data is a type of frequency distribution called a contingency table. A contingency table, also known as cross-tabulation or crosstab, shows the number of observations in each combination of groups. It is usually includes row and column totals. Examples, contingency table. 6 months after the intervention, The city looks at the outcomes for the 300 households. Only 4 households are shown here. Examples of contingency tables is ang table nga nabilang sa household address, intervention, tag outcome. Tatlo na sila. Anong ginatawag sila? Rows. Tapos, ang household address, ang combinations of group nila mo ni sang ML Street, Cedar Street, Maple Street, Oak Street. Ang sa intervention, ang combination sang groups nila mo ni sang flyer, control, phone call. Ang sa outcome, amo ni silang recycles, does not recycles. Ang sa household address liwat. Ang sa ML Street, ang ila intervention is flyer. Ang ila outcome recycles. Sa household address, ang Cedar Street, ang ila intervention control. Tapos ang ila outcome ma-recycles. Sa Maple Street, ang ila intervention amo na ang control. Ang ila outcome does not recycle. Ang sa household address, Oak Street, ang ila intervention phone call naman. Tapos ang outcome recycles. Kag ang column amo na sa ang mga combination of groups. They reorganize the data into a contingency tables. Amo naman na sila nga i-organize liwat ang data pakadto sa contingency table. Way back gali sa contingency table ang kon explain ng dra ta makita ang results sang data na ginapangita ta kag isa ni sa ka-type sang frequency distribution. It means gina-distribute ta ang given na data nga para maging organize ang aton na table kag ma-include man naton ang rows kag column manamot sa paginang ginambal ko nga rows kag column nang mabalik taliwat sa they reorganize the data into a contingency table. Ang sa intervention, ang combination of group nila mo ning flyer, pamphlet, phone call, controls, column, totals. Sa diri naman niya sa kung mag-reorganize ka sang data, itabulate na ang score sang data sang given sang contingency tables. Tapos nang apat ni siya gali ka rows amo ni sang intervention niya ang recycle kag does not recycle kag rows total. So ang intervention flyer pamphlet ang iya nga recycle is 89 tapos ang does not recycle 9 row totals. Ang row totals niya is i-add mo lang ang flyer nga recycle kag sa does not recycle 8 plus 9 equals to 98. Tapos sa phone call ang iya recycle 84. Ang iya nga does not recycle 8. Bali total mo naman sila liwat. Ang magwa siya nga score is 92. Sa control naman ay sa intervention nga control is 86. Ang iya recycles and does not recycles is 24. I-add mo muna sila Japon ang row total nila is 110. Tapos ang sa column total amo na siya ang i-add mo ang kung pila ang ilang recycles isumaon mo nan ang ilang recycle is 89 plus 84 plus 86 is equals to 259. Sa column totals naman sang does not recycle is ang number yan 9 plus 8 plus 24 is equals to 41. Tapos magkuha ka naman yung row totals sa column totals i-add mo ang iya recycle kag does not recycle nga column totals. Ang sa recycle na-add tanan is 259 ang results kasi does not recycle is 41. Bali ang column totals ang n nga ginapangita is 300 ang iya. So ang row totals ya is 300. How to calculate the test statistic formula? Chi-square is the test statistic for the chi-square test of independence. X squared is equals to ang E, amo na sa summation sang operator, it means take the sum of. Tapos, ang O is the ang O nga symbol is the observed frequency. Ang E naman niya is the expected frequency.
Follow these 5 steps to calculate the test statistics. Step 1. Create a table. Create a table with the observed and expected frequencies in 2 columns. So, intervention, outcomes, observed frequency, and expected frequency. As bali ang observed frequency, given na ni siya. Then, ang expected frequency, makuha ni siya by i-multiply tas ang row kag ang column total. So, row total times column total divided by the grand total. So, 98 times 259 divided by 300 equals 84.61. 98 times 41 divided by 300 equals 13.39. Then 92 times 251 divided by 300 equals 79.43. Then 92 times 41 divided by 300 equals 12.57. 110 times 259 divided by 300 equals 94.97. Last, 110 times 41 divided by 300 equals 15.03. Then, step 2. Calculate O minus E. In a new column called O minus E, subtract the expected frequencies from the observed frequencies. So, isubtract ta ang expected frequency from observed frequency. So, 89 minus 84.61 equals 4.39. 9 minus 13.39 equals negative 4.39. 84 minus 79.43 equals 4.57. 8 minus 12.57 equals negative 4.57. 86 minus 94.97 equals negative 8.97. 24 minus 15.03 equals 8.97. Then step 3. Calculate O minus E squared. In a new column called O minus E squared, square the values in the previous column. So, square ta ang O minus E ang minus tagina. So, 4.39 times 4.39 equals 19.27, same as negative 4.39. 4.57 times 4.57 equals 20.88, same ang Japon sa negative 4.57. Negative 8.97 times negative 8.50, negative 8.97 times negative 8.97 equals 80.46, same man sa 8.97. Then step 4. Calculate O minus E squared divided by E. In a final column called O minus E squared divided by E, divide the previous column by the expected frequency. So i-divide the C O minus C squared kay expected frequency. So 19 divided by 27, 19.27 divided by 84.61 equals 0.23. 19.27 divided by 13.39 equals 1.44. 20.88 divided by 79.43 equals 0.26. 20.88 divided by 12.57 equals 1.66. 80.46 divided by 94.97 equals 0.85. 80.46 divided by 15.03 equals 5.35. Step 5. Calculate chi-square. Finally, add up the values of the previous column to calculate the chi-square test statistic. So, ipang-add ta ni tanan. Ipang-add ta ni sa. Chi-square equals 0.23 plus 1.44 plus 0.26 plus 1.66 plus 0.85 plus 5.35 equals to 9.79. So, amo ni siya aton chi-square, 9.79. Then, how to perform the chi-square test of independence? If the test statistic is big enough, then you should conclude that the observed frequencies are not what you'd expect if the variables are unrelated. But what counts as big enough? We compare the test statistic to a critical value from a chi-square distribution to decide whether it's big enough to reject the null hypothesis that the two variables are unrelated. This procedure is called the chi-square test of independence. Follow the steps to perform a chi-square test of independence. The first two steps have already been completed for the recycling example. Step 1. Calculate the expected frequencies. Use the contingency table to calculate the expected frequencies following the formula. So, nakuha ta na kagi ng expected frequencies sa amo ni siya nga formula. Step 2. Calculate chi-square. Use the chi-square formula to calculate the test statistics. So, nakuha ta naman isa ang chi-square, which is 9.79. Step 3. Find the critical chi-square value. You can find the critical value in a chi-square critical value table or using statistical software. You need to know two numbers to find the critical value. The degrees of freedom for a chi-square test of independence. The degrees of freedom is number of variable 1 groups minus 1 times number of variables 2 groups minus 2. Significance level. By convention, the significance level is usually 0.05. Example, finding the critical chi-square value. Since there are 3 intervention groups, flyer, phone call, and control, and 2 outcome groups, recycle and does not recycle, there are 3 minus 1 times 2 minus 1 equals 2 degrees of freedom. So, aton degrees of freedom is equals to 2. For a test of significance level equals 0.05 and degrees of freedom equals 2, the chi-square critical value is 5.99. So, chi-square, amo ni aton chi-square distribution table. Aton degrees of freedom is 2, then aton significance level is 0.05. So, ari aton critical value 5.99. Then step 4. Compare the chi-square value to the critical value. Is the test statistic big enough to reject the null hypothesis? Compare it to the critical value to find out. Chi-square equals 9.79. Critical value equals 5.99. The chi-square value is greater than the critical value. Step 5. Decide whether to reject the null hypothesis. If the chi-square value is greater than the critical value, then the difference between the observed and expected distribution is statistically significant. The data allows you to reject the null hypothesis that the variables are unrelated and provide support for the alternative hypothesis that the variables are related. If the chi-square value is less than the critical value, then the difference between the observed and expected frequencies is not statistically significant. The data doesn't allow you to reject the null hypothesis that the variables are unrelated and doesn't provide support for the alternative hypothesis that the variables are related. Example, deciding whether to reject the null hypothesis. The chi-square value is greater than the critical value. So therefore, the CT rejects the null hypothesis that whether a household recycles and the types of intervention they receive are unrelated. So kay mas dakwa aton chi-square value kaysa sa critical value. So rejects naton ang null hypothesis. This is a significant difference between the observed frequencies and the frequencies expected if the two variables were unrelated. This suggests that the proportion of households that recycle is not the same for all interventions. The city concludes that there are interventions have an effect on whether households choose to recycle. That's all. Thank you.